We exist in a universe filled with complex, mind-boggling structures, which begs the question, how did all this stuff come about? In this video, we'll wind back time to the universe's first moments and explore each step in its evolution. Today, origin of the universe. Current models describe reality as particles that move about and interact. Among others, these include electrons and quarks, which combine to make protons and neutrons. These particles are not classical solids. Instead, they are localized excitations in underlying quantum fields that permeate all of space. Even in an empty region, the fields exhibit fluctuations which produce measurable phenomena, such as the Casimir effect. The fluctuations are called virtual particles. They can be likened to ordinary particles, which would keep popping in and out of existence everywhere. By exchanging such virtual particles, ordinary particles can interact. Virtual photons, for example, carry the electromagnetic force. This is our most accurate description of the universe to date. Quantum field theory. We'll explore its details in a future video. That said, to understand the origin of the universe is not to simply explain how particles emerge, but to explain why the underlying fields themselves exist to begin with. Why is there something rather than nothing? Alas, current theories cannot yet clearly solve this fundamental question. Nevertheless, we'll attempt to approach an answer by resorting to some speculation before jumping back to the concrete physics. Indeed, the simplest scenario is that nothing at all should exist to begin with. However, this overlooks another possible reality that's just as simple. Instead of nothingness, it's a reality filled to the brim with an infinitely hot, infinitely dense amalgam, a sort of fluid which abides to certain fundamental symmetries. And it's some quantum dynamics in this fundamental fabric which would be behind the physical properties of the universe, its laws of physics. We now know that this was the state of the universe in its very first instant, just short of the singularity. An inside observer would measure this event to have taken place 13.7 billion years ago. Hopefully we won't have to wait long for the real answer. Our current fundamental theories of physics become accurate just fractions of a second after the Big Bang. Before we proceed, it is important to understand a certain notion. The popular Big Bang depiction, which shows a small expanding sphere, can be misleading. Subtle clues indicate that the universe is likely infinite in size. However, light from stuff located too far away from us hadn't yet had enough time to reach us since the birth of the universe. All we can see thus lies within an ever-growing sphere, the observable universe, currently 93 billion light-years in diameter. What the traditional depictions illustrate is the observable universe. They seem to imply that the universe is empty outside the expanding sphere, even though, in reality, that's not the case. The universe was always infinite in size, ever since its first instant. The Big Bang occurred everywhere at once, starting with an infinitely dense universe which expands and cools over time. The first 10^30th of a second makes the Planck Epoch. This period is still very poorly understood. Temperatures were so ridiculously high that our current theories break down. Our best educated guess is that the four fundamental forces, gravity, electromagnetism, the strong force which binds the nuclei of atoms, and the weak force responsible for certain types of decays, did not manifest yet. Instead, a single unified force existed. The intense energy densities induce negative pressure, causing the universe to expand. As it expands, the intense energy spreads out and temperatures go down. At the end of this epoch, as temperatures cross a certain value, about 100 nonillion degrees, a phenomenon called symmetry breaking occurs. Similar to a phase transition in ordinary matter, the quantum fields start to behave differently, and the force of gravity as we know today manifests, leaving the other three forces as the grand unified force. Active research is still trying to work out its details. This marks the grand unification epoch. At an undecillionth of a second, once temperatures cross 10 octillion degrees, the second symmetry breaking occurs. Once again, the fields start behaving differently. The strong force manifests, leaving the electroweak force and marking the start of the Electroweak Epoch. It's at this point that our established theories start to apply. Electroweak unification has already been solved. Around this time, the universe starts expanding at an extremely fast rate in a process dubbed inflation. In just a nonillionth of a second, a region smaller than a single proton would have instantly expanded to a size larger than the solar system. The minuscule quantum fluctuations inflate along into large regions of varying density, which will later seed the formation of galactic filaments. Due to this drastic decrease in energy density, the universe starts to calm down. Conditions become just right for the violent activity in the underlying quantum fields to decay into localized excitations, forming elementary particles. Among them are electroweak bosons, gluons which mediate the strong force, and whale fermions, precursors to today's matter particles, such as electrons and quarks. Essentially, the energy which was driving inflation decays into a superheated quark-gluon plasma in a process dubbed reheating. This phenomenon, where particles emerge from pure energy, can be probed today in particle colliders. Giant machines which smash particles together at near light speeds, shocking the surrounding quantum fields and causing new particles to appear out of seemingly nothing. At the trillionth of a second and a temperature of a quadrillion degrees, the final symmetry breaking occurs. Some particles start interacting with the surrounding Higgs field, slowing them down, or in other words, giving them mass. These particles include a few of the weak force carriers, causing it to differentiate, leaving the electromagnetic force carried by massless photons. However, the particles are still too agitated to feel the effects of any of the fundamental forces and remain in plasma form. This period is thus called the Quark Epoch. The universe continues to expand and cool down. At the millionth of a second, the particles become calm enough, and the strong force starts to dominate. The tendency of particles to interact with force carriers is prescribed as a property, their charge. Similar to the electric charge, which has two opposed elementary values, the charge of the strong force, which prescribes the tendency of quarks to interact with gluons, has 6 elementary values. Because they can add up in a similar way to traditional color theory, these charges were dubbed color charges: blue, red, and green, and their antimatter counterparts: anti-blue, anti-red, and anti-green. As groups of quarks with complementary color charges get close, they start constantly exchanging gluons, keeping them under constant attraction. Beside their color charge, quarks can also interact with photons. They have fractional electric charges. 2 up and 1 down quark make a proton with a combined charge of 1. And 1 up and 2 down quarks make a neutron. Everywhere, the quarks start assembling into groups of 3. The universe transforms into a plasma of protons and neutrons, collectively called hadrons, and their antimatter counterparts with opposite electric charges, with electrons and positrons swimming around. This is the Hadron Epoch, which spans until 1 full second after the Big Bang. When particles form, they always emerge in pairs of 2 with opposite electric charges, matter and antimatter. And when a particle and its antiparticle collide, they annihilate, leaving only electromagnetic energy in the form of photons. During this epoch, hadron-antihadron pairs constantly form and annihilate. But towards the end, the universe cools down and new particles stop forming. Most hadrons annihilate, leaving mostly the electrons and positrons to dominate. This marks the Lepton Epoch, lasting a few seconds, during which electron-positron pairs went through the same process of formation and annihilation. By the end of this epoch, around the 10-second mark, most of the matter and antimatter had annihilated, leaving only a small fraction of the matter left, due to a slight difference between the amounts of set two opposites. This difference is dubbed baryon asymmetry. Its cause is still a mystery, though few candidate explanations do exist. At this point, the entire universe resembles the inside of a star. What would eventually make up everything in the observable universe was condensed within a sphere perhaps the size of just a few galaxies. It was still so hot that the agitated hadrons collide and fuse into heavier elements, forming hydrogen and helium isotopes, as well as a few other light nuclei. Theoretical models predict certain proportions between the amounts of the different elements, which can still be seen today in interstellar gas. This period, called Big Bang Nucleosynthesis, lasted 17 minutes, by the end of which fusion halts, and the universe lingered in the same state for a few 100,000 years, slowly expanding and cooling. This is called the Photon Epoch, dominated by photons left over from annihilation and fusion. Gradually, the universe settles down, and the effects of the electromagnetic force start to become noticeable. The positively charged atom nuclei capture the negatively charged electrons in stable orbits, finally forming full-fledged atoms. This event is called recombination. It took place when the universe was over 370,000 years old. Unlike in their plasma states, these gases don't interact with most photons. They are transparent. It is at this point that the light, which would eventually be captured by our telescopes to form the cosmic microwave background, started propagating towards us, making up our earliest possible visual of the early universe. At this stage, the universe was an endless dark void filled with very hot hydrogen and helium gases, which will eventually bunch up into stars and galaxies under the effects of gravity. We'll explore this in the next video on star formation.